everyone, so today we'll be learning about the Kohn-Sham self-consistent field. The Kohn-Sham approach is to introduce a fictitious auxiliary system that aims to somehow mimic the real multi-electron system we are dealing with. This fictitious system is a set of particles with the same properties as electrons, except that the repulsive electron-electron interactions are turned off. The particles move in some fictitious external potential called the Kohn-Sham potential, which is defined so that the ground state density of the system is equal to and the same as the density of the electron system we are evaluating. This assumes that the true ground state density is actually also the ground state density of a non-interacting system. Since the particles in Kohn-Sham system do not interact with each other, the ground state wave function of the system is far less complex than that of a real interacting system. Now let's take a look at the Kohn-Sham equation. In the Kohn-Sham equation, the first term is the electron's kinetic energy. The second term is the interaction between the electron and the nuclei. The third term is describing the interaction among electrons, and the fourth term is the exchange correlation potential. The third and the fourth terms are the functional of the electron density. So in order to set up the Kohn-Sham equation, we need to have knowledge of the system's electron density as input. The first step to approach this method is by choosing an appropriate basis set. Higher basis set can provide more accurate results but would require more computing time. The second step is to choose a molecular geometry. The Kohn-Sham operator depends on the molecular orbitals which we seek. Therefore, an iterative procedure needs to be used to find these orbitals. Next, we will proceed to the SCF loop. So we first have to compute and store all overlap and one-electron integrals before proceeding to the next step, guessing initial electron density (NR). For the next step is guessing initial density matrix. Since a material is composed of atoms, it is reasonable to approximate the system's electron density as the superposition of the electron densities of constituent atoms. Then, we calculate the Kohn-Sham potential that depends on the electron density. With these terms computed, we can then set up and solve the Kohn-Sham equations by using the initial electron density to get a single particle wave function. From step 5, the output electron density defined by the Kohn-Sham single particle wave function is computed. Thus, we obtain a new electron density. Now, we can compare the new electron density obtained with the initial electron density. If they are the same or very close to each other, we say that the convergence is reached, and thus this is the ground state electron density. It can then be used to compute the total energy or other physical quantities such as force, stress, band structure, and density of states. If the initial and output electron density are very different, then we say the convergence is not reached. Therefore, we have to feed the output electron density to the beginning of the SCF loop and calculate the new electron density again. Finally, if you wish to optimize the geometry for the molecule, you may continue with if either current geometry satisfy the optimization criteria or not. If yes, then the output data can be obtained. If not, you will have to choose a new geometry that satisfies the optimization and return to the SCF loop again. That's all from us. Thank you.